in English than I am in French. Or I can do it in German. Every Swiss speaks German fluently. So, having heard nervous laughter, I'll stick with English. So, what is a trap? You see the poor mouse here stuck in the trap. So, in the context of a programming language, a trap is code that compiles, and it links, and it executes, and then it does something different than you think. Now that's of course something that you have great experience with as C and C++ programmers, and it's useful to look at some of these traps. But so let me first look at an example though. So have a look at this code here. So here we're checking whether x is between -0.5 and 0.5, and if so, we return 0. Or do we? What's wrong? Yeah. So let's say x is a double. So it does in fact not test whether x is between -0.5 and 0.5. Even though it looks like it, right? Because if you look over here, -0.5 less equal x, that's an expression, right? And it's expression of type bool. Now in most programming languages, the compiler would now say, well, look, this thing here is a bool. The thing on the right is a double. And it never makes any sense to compare a bool and a double. I mean, is true less than 0.5? I mean, that's a silly question. There are only 2 programming languages ever created by man where this compiles. Those 2 languages are the 2 languages that you have the misfortune of having studied the last year. So that is C and C++. Those languages have the totally idiotic notion of saying that a bool, something that should be true or false, can be automatically converted to 0 or 1. And so the C or C++ compiler will do that conversion. It will take the thing on the left, convert it to a 0 or 1, and then it'll check whether that 0 or 1 is less equal than 0.5. That check never makes any sense, but they will do it anyway. So that's disgusting. Why do they do that? What possessed the designers of C++ to allow it that such a disgusting statement gets compiled, and that it runs, and that it produces a result that makes no sense? So is it efficiency? Is it ignorance? And the reason is it's history. So at one point, people programmed either in a high-level language, such as ALGOL, or they're programmed in assembly language, machine code, low level. And then people said, we would like to program efficiently, but machine code is tedious and it's not portable. And so C was invented as kind of a minimal language that gave you some features of a high-level language with still having all of the control that you have at the machine level. And it was meant to be like the simplest language possible that would let you program close to the machine, like in an operating system, or in, at that time, computers were tiny, computationally wise. The computer, you would pay 50,000 francs for a computer, so the computational power was tiny, the size was large. They would be this large, and they would have the computational power of a toaster oven. It's something like my phone. It would be unimaginable 30 years ago. You know, the computational power of this phone would fit, you know, you would have had rooms and rooms of mainframes to accommodate that computational power. So at that time, it made a lot of sense to say, hey, we need to program these devices that have little computational power. We need to do it as fast and as efficiently as possible, but we don't want to do it in assembly. And that's how the C language was invented. The people who invented the C language were not gifted language designers, as you can tell, having used that language for a year. They just wanted to have something simple that worked. They were not concerned with Boolean values. They just said, we don't even want to invent a new type. We have other things to do in our life than inventing a Boolean type. We'll just make 0 stand for false and 1 stand for true. And that's how C was for a long time. And it was very, very successful at what it was doing. Everyone programmed in C because it let you program those machines. You could access all their power, and you had a little bit of the comfort of a high-level language. Then came C++. And so the designers of C++ said, we want to have a programming language that lets you do large-scale projects, very large programs, object-oriented programming, and then they said something very strange. They said, and we'll build it on top of C. That's like saying, I want to build a mass transportation system that can transport millions of people all over Switzerland, and I want it to be based on the Fiat Cinquecento. So this made no sense. But nevertheless, by historical accident, they more or less succeeded, and so we're all stuck with this. So in C++, they said, well, of course we're going to have a Boolean type, but because of backwards compatibility with C, we have to allow that crazy conversion, and that's what makes this pitfall. So understanding why it's there, I think, helps you look out for the pitfall. You know, someone who just comes from no particular programming background at all will say, you know, why are they torturing us like that? But there's a historical reason for it. So why do we study traps? So you see these two cute little raccoons. They study this trap that some evil farmer put there to trap the raccoons. And of course, they're keenly interested in understanding its mechanism. Their life depends on recognizing a trap. And so does yours, right? So you want to know when to be careful, when to be very careful. You want to know what to avoid when you use a language. So someone says, you shall be programming in C or C++, and you want to know what the risk of that is. You also want to know when selecting a language. So when time comes for you to start a new project, and you want to know, do you really want to do it in a particular language? I'm telling you about traps in C and C++. I could tell you about traps in JavaScript or in PHP. And when you use any of these languages, you want to know, is the trouble, is it worth it? Do you get more benefits from the language than you expend in being very careful? And finally, maybe some of you will actually end up designing a language. People turn into language designers who never think they would ever do this, like the people who designed C. They were clearly not language designers by education, the result shows. But nevertheless, there they were at a point in time, and they designed a language. Another language that clearly was done by someone who had no business ever designing a programming language would be PHP, right? Clearly designed by a bunch of monkeys who were locked in a room overnight. So it might happen to you that you need to design a language, and at that point it would be nice if you had some idea of what is good and what is bad about language design. The other reason I like to give these talks is that some students don't really think about the fact that languages are engineered by humans and that they are not perfect. But it's a very good perspective to understand that, because when you know the weaknesses of what is a human creation, then you can approach it quite differently than when you think this is something that has always been like that is unavoidable. So, a little bit of warm-up so that you recognize a few of the simpler traps. And so have a look at this. And my question is, what's the trap? So let me ask a simpler question. What is the value of y? So we have x is 3, p is the address of x, y is, so it says x divided by star p. What's star p? Aha! Who said it's a comment? Very good. It is a comment. See? X / asterisk. This is the start of a comment. The comment extends all the way until here. And then you have the semicolon. Now, in a normal programming language, this would not have compiled, because in a normal programming language, comments nest. That means when you have a comment that goes from here to here, and now you put this into another comment, in a normal programming language, the big comment would enclose the small comment, and when you have a thing here and a thing here and only one closing one, something would go wrong. Why is it desirable for comments to nest? Yeah? Yeah, you want to comment out a large part of stuff, right? This is just a basic human urge, right? You have a whole bunch of code and you hate it and you want to get rid of it temporarily. You put a comment around that. In C, not so much, right? Because the designers did not make it so that comments nest. Why? It's simple, basic incompetence. So every language before and most languages after, the comments do nest, but in C they don't. All right, here's another amusing example. So here we have a negative number, -2. So you may remember that if you have 32-bit numbers, that this thing here masks out the sign bit. So here I'm looking at the top bit, and if that bit is 1, then my number is negative. What's the trap? I think they're on the right track there. Yes? No, you.
No, I was just asking if the first character next to the 0x is still 0 because I read 8. If it's 0, it's 8.
Oh, that's an 8. Yes, that's an 8.
It's 8.
Yes. But what's the trap? Yeah.
There's no guarantee that two components of you expect.
Well, let's say this happened somewhere on Earth.
And no guarantee about the then.
No. But let's say it's 32-bit. I mean, this is we're in the realm of low-level programming here, right? So we're going to assume that it's a 32-bit architecture. It is a two-complement architecture. Yes? Very good. Okay. For some reason, not equal binds stronger, so this stuff gets computed first. And it's going to check, is 0 not equal to 0x8000? And the answer of that is true. Can you take an integer and take the bitwise AND with the Boolean? Yes, sir, and see you can. Because what happens to true? It gets converted to the integer 1. So instead of ANDing with the top bit, it fishes out the bottom bit. Now, what went wrong? Some bunch of people said, we're going to be building a new language. We're going to be putting in a bunch of operators, such as plus and minus and times and over, like we've always said, and equals and not equals, and less than, and so on. But this is a language where we also want to be able to access every bit because we're building a language for low-level programming, for replacing assembly language. So of course we want to have, you know, bitwise and, bitwise or, and bitwise not. And just because we don't know any better, we're going to give stupid precedences to these operators. So they could have thought this thing through, that when you want to and something, that afterwards you want to test whether it's equal to something. But they didn't. And by the time that they found out, it was too late. Because there were already many thousands of lines of code written in this language, and they couldn't be bothered to change it. And so now, billions of lines of code later, we still have this problem. All right, here's another simple pitfall. What's wrong here? Yes?
There is a semicolon at the end.
Very good. Excellent. You guys are good. So, there's the semicolon here, right? And so this is unfortunate that they designed it, the if statement in this way. So if you look at some other language, for example in Python, you know, where you would say if a I greater max, and then the next line you indent, and the indentation shows what the scope of the if is. That's a much better arrangement. Or if you look at the arrangement, oops, that happened in Algol 60, a language that preceded C by, by 15 years or so. There it said if I greater max then, and the then guided the translation. Those were all very good ideas. To just put the if and then the parentheses and then allow the semicolon as an empty statement, maybe not so good. So you have these syntactical issues that are an annoyance for everyone who learns C++ or C. And most of you have learned them more or less, and you know that they're there. But it gets worse. So let's look at this issue here. We want to check whether x is odd. If you know x is even, if you do mod 2, then it's 0. If the remainder by 2 is 0. So it must be, to test whether it's odd, we should be able to check if the remainder is 1. Is that right or not? So will this test for odd numbers? You know, 1, 3, 5, 7, 9, and so on?
Maybe the same than before, and 2 equals 1
No, actually in this case, a very, very good question, but see, that's what happens when we get so nervous, right? And some people are so nervous they put parentheses everywhere. Nothing wrong with that. But in this case, the percent does bind stronger. It really will compute x mod 2 first, and then check whether the remainder is 1. What if x is negative? What is minus 1 mod 2? It is minus 1. Okay? For any negative x, if you take the remainder, it is minus 1. Now, this is very annoying. So, and I'll give you, this is annoying every time you want to use the remainder. And I'll give you kind of a realistic example on why it's annoying. So let's say I have some value of degrees. And so I have degrees, and then I rotate it a little bit more. Maybe I'll go backwards. And now I have some value of degrees that maybe is 1,000. And I want to get it back to between 0 and 359. And normally you would say, oh, then all I have to do is do mod 360. And now I have a value between 0 and 359. But if degrees is negative, then I would have a value between minus 1 and minus 359. And if I want to normalize it, then I have to do some icky stuff. So what works is, if I always add 360, then I get a value between 0 and 720. And then if I take another modulus, then it actually is right. Now it's weird that one has to do this. And one also has to do this when you do minutes and seconds and hours, when you do like a digital clock. This negative numbers where you take the remainder, it always is a stupid and annoying issue. And now, why did they do this? And the reason is it was plain ignorance. This is not something where the designers of C can be faulted for, but the people who did some hardware that preceded C by about 5 years, they needed to implement the modulus operator in hardware. Now, you would think that they could have looked up, maybe I have an explanation. Wikipedia didn't exist then. So they would have actually had to go to a library and open a math book. They didn't. So the mathematicians for about 300-400 years knew how to do this right. And they said a remainder is always positive. A negative remainder makes no sense. It makes all sorts of computations uncomfortable and unwieldy. We shall define that the remainder is the smallest non-negative number such that. And these guys just didn't bother to open a math book. So that's unfortunate. Programming languages can fix this. Python, for example, at one point said, we've done this stupidly for 20 years or so, and in Python 3 they fixed it. They introduced an operator that does the right thing. So here's another thing. One of the things that C is kind of typical for, and that is a selective feature, is things like printf. Printf is actually pretty cool, because remember how you have to do this stuff in C++ with cout and set precision and set w, and it's all kind of a mess. And so printf is simple. You give this little pattern, and then you print. So what does this print? So %d is a decimal number, %s is a string. Does it print 0.5 liter? D is for integers. Cleverly selected because the word integer does not contain the letter D anywhere. So what will it do? Will it convert 0.5 into an integer? No, sadly it will not. Here's what it'll do. So somewhere in memory, where the 0.5 is stored as 8 bytes, with a bunch of bits, I don't know how 0.5 is stored, the first 4 bytes of this will be interpreted as a decimal number. And it looks like this. So that, and then of course it messes up the liters completely. And so what happens is on the stack, it has now pushed an 8-byte quantity, of which it prints the first 4 bytes, and then afterwards the address of a string. And so the %d will say, okay, I'm going to print the first 4 bytes. Then I'm going to take the next 4 bytes, which by the way happen to be the remaining 4 bytes of this floating point number. I will say, oh, that must have been the address of a string. I will follow that string and type the characters that are there, which apparently are these unprintable characters. So that is very dangerous, right? So these variadic functions are super, super dangerous. And it gets worse with scanf, right? So what happens here? What's the error? This must have happened to every one of you. Huh? Yes, yes. Exactly. Huh? There's a missing ampersand, right? What happens when you run it? Yeah. But, so when I ran it, I had a good day. And the program died with a segmentation fault. And you might say that's terrible. But what is worse than such a program dying with a segmentation fault? There's only one thing that is worse than dying with a segmentation fault. Yeah. And that is not dying with a segmentation fault. Right? Because then it would somewhere overwrite something and you have no idea where that is. So a segmentation fault is actually a good thing. Every time you see a segmentation fault, you should say thank you, because the alternative is not having the segmentation fault. The alternative is that the program runs fine for you, and then you give it to your professor or to his assistant, and it runs with a segmentation fault or worse. So a segmentation fault at least shows you that something is wrong. But here the problem is that scanf and printf have no way of checking what is there in those variadic functions. Now, of course, with a modern compiler, in these cases you will get a warning, because those compilers have hardwired knowledge about printf and scanf. And so it's safe to use printf and scanf as long as you use such a compiler. Every other function that is variadic, where you can pile in other things on the stack, I'd stay away from it. Those are dangerous things. All right, another thing about the C language that you've all come to love, and it's interesting to know why one has this issue, is these incomprehensible declarations. It starts simple enough. Here we have an array of 10 car star. Not a problem, right? Car star, lines 10. Here we have a pointer to an array of 10 elements. That's a little worse. Why the parentheses? Yes, so that's a single pointer, because otherwise, right, it would be the same thing here. Otherwise, it would be a car star row of 10, and that's an array. And so then you have to put the pointer here. It gets worse, right? What is this? This is a pointer to a function. A pointer to a function consuming an integer and yielding a string. Okay. This thing is something that actually exists. This is the declaration of the signal function. And I have no idea what it is. I mean, I could figure it out. I have a PhD. But, but it's totally ridiculous. And so the reason this is because the C and C++ language, and of all languages designed by humans, only the C and C++ language, have this crazy idea that some modifiers are put after, like the stars, and some of them are put before, and some of them are put in between somehow. And so instead of doing what other languages do, where everything goes left to right. So in Pascal, for example, I'm just paraphrasing this a little bit, you would say I have an array of length 10 of pointers to character. Notice how it goes left to right. Array of size 10 of pointers to character. Here I have a pointer to an array of size 10 of characters. Here I have a function consuming integers, yielding a pointer to a character. But here's signal, which is a function that consumes an integer, and it consumes another function, and it yields a function, which actually is what signal does, strangely enough. So, but you can figure it out because it's all left to right. So interestingly enough, this idea has been around forever, since ALGOL. ALGOL was designed in 1960. And so, way before almost anyone in this room was born, except me. I was 1 year old. And so ALGOL did a lot of these things right. There's a famous saying that's worth knowing by Hoare, who said, here is a language that was so far ahead of its time. There was not only an improvement on its predecessors, which were pretty bad, but also on nearly all of its successors. And so the designers of C would have been well advised to have a look at ALGOL and to imitate some of its stronger features instead of just doing some random stuff. All right, but that's just syntax. Syntax it's not pleasant that a language has silly syntax, but it is something that we know from 50 years of social science, that programmers can adapt to any syntax. The social science was simply to invent C and to have people use it. And so people have survived. But let's move on to semantics, to the actual behavior. So here I have a very typical kind of thing that you will often see. Now I have an array and I want to swap its neighbors. I'm doing this in C because that's our first programming language. And so I want to swap this guy and this guy and this guy and this guy. So I take pairs of elements and swap them. So we'll assume that swap is a function. I guess it would have to be a C++ function here that does the swapping, because I need reference parameters here, right? What's wrong with the function? What's that? So can I ever get out of range? I think you said out of range. When? At the end. Can something bad happen at the end, right? And so the good thing is that everyone is nervous about the end, right? So let's say we have 10 elements. Then in this case I is less than 10, and so in the last one we swap 8 and 9. Which is okay. So in this case I would be it goes up to less than 10, so the most it can be is 8. But when can you run over the edge? What if it was 11, right? What if you call this and n is 11? Then it will swap the 10th one with whatever happens to be behind, which could be very bad because there's a good chance that whatever happens behind, could be an important piece of information for the memory allocator, or who knows what is there. So this could be quite bad. Now, why is that so? So what happens is that, as you know, that's how arrays work, right? You get a pointer to the start, and it is not possible to know where the array ends. And this is something that gives you a lot of grief in C programming and in C++ programming. So why does the array not know where it ends? Why did they make it like that? What do other languages do? Like, did you have Java yet? No, right? This is the trouble when you start out with C. So in Java, what happens is when you pass an array, the receiving function gets a data structure that perfectly well knows how long the array is. And when you say a bracket I, and I is out of range, then there is a runtime error right then and there. Yeah? Right. So it was for efficiency, right? So C was supposed to be as efficient as possible. It costs time and money to do the range checks. And so in C they said, in assembly we don't have range checks. So in C we don't need them either. And that makes perfect sense if you program the control software of a toaster oven. For everything else it makes no sense whatsoever. These are very common errors. There are attackers every day who try to install viruses on your computer that exploit these kinds of errors. And so it's a huge, huge problem. So for you that means that there are two reasons to use arrays in your life, C arrays. So if you program in C or in C or C++, there are two reasons why you might want to use an array. The first reason is that you only have C. If you only have C, you have no choice. You want to collect stuff, you have to use an array. And you might only have C because you're programming for an embedded system and you want to really conserve all possible resources that C++, who knows what gets introduced, or you program an operating system, and so you absolutely want maximum efficiency, and C is your weapon of choice. Then, of course, you use an array. What is the other reason? Let's say you have C++ at your disposal. Why would you want to use an array? Exactly, because your instructor makes you. That is the only other reason ever to use an array. Don't use an array. Use a vector. Right. There's no rational reason ever for anyone to use an array except because your instructor makes you. So if you have your choice, by all means use a vector. Vectors you can use @. @ is safe, and it gives you a decent error message. You can, if you want to use brackets, there are implementations of vectors where the bracket is range checked. Vectors are fairly sane. They can be sane. By default, maybe they're not totally, but you can work with vectors. Yeah?
We need the smallest amount of memory usage, for example, in a little.
Exactly. And if you have a little device, credit cards, computer or something, then you would use C and then you would use arrays. So so they're not doing the wrong thing here by teaching it to you. There are times when you need to do it. But when you have the choice, when you program like stuff on a bigger computer where you don't need the efficiency, a vector is a safer choice. And so arrays, really only when the risk for using arrays is huge. You have this unconstrained pointer. You have to control every aspect of it. It's very dangerous. We know it's dangerous because people have been doing it for 40 years. And why do you think that Windows downloads 20 security patches every time you turn on your full computer? It's because somewhere out there was yet another buffer overrun that needed to be fixed. And so don't do it. There's no reason to use arrays except to learn how arrays work and to if you're really only doing C. So if you're on a desert island with nothing but a C compiler, then you use C and then you use arrays. That's the rules of the game. When you use C++, why there's the cost difference between arrays and vectors is so small that in almost all cases you should just use the vectors. So that brings me to another very interesting question. One of the nice things in a modern programming language is you get a large library, so you don't have to reinvent everything. So, for example, in C++, did you guys talk about STL at all? Okay, so I'll tell you about STL, then you'll learn something. So there is a library called the Standard Template Library in C++ that has about 100 functions that do use full stuff. For example, find will find an element in a collection, in a vector or whatever. There's a function called random shuffle that will randomly shuffle all of the elements in case you want to implement poker. That way you don't have to implement that. There's a function sort, of course, that sorts the elements, so you don't ever have to implement a sort algorithm. Why do they teach you sorting in ASD? When you could just call sort? Because it's good for you. So, no, I mean you want to understand how these algorithms work, right? But so in practice, you would always call sort, and so all of these things, there's something to find the maximum, to find the minimum, to find something given a particular condition. You just pass the condition as a function pointer. So the standard library is something that is well worth knowing about because a function that you call is always better than a function that you write, because it has a much higher chance of being correct. And and that holds for everyone. Holds for me just as much as for you. So they give us a function find, and here's how you find something in a vector. You give it the begin. You guys never talked about this. Okay. You give it the begin, you give it the end, and then you get back an iterator that's kind of like an advanced pointer that points to the thing where it has found it. But now there has to be a way of finding out whether it found it at all, and if it didn't find it, then you're at the end. So b.end is the end of the iterator. And so here's what my little piece of code does. So I have my vector here. I'm looking for inside there some number, say n is 42. And if I found it, then p gets sent in here. Then I wipe it out, put in a -1 instead. And also I'm taking it and putting it at the back of A for whatever reason. So that's what my code does. But there's a little typo in here. Did anyone spot the typo? Yep. For some reason, it says b.begin and a.end. The compiler cannot catch that, because b is a pointer or an iterator, a is a pointer or an iterator, and it cannot catch it. And so when I ran it, unfortunately, it didn't dump core. it overwrote some memory location somewhere with -1. I have no idea which, and my program was over before it could cause any damage, but in real life, of course, it could, right? So it should have been b.end. Now, you would think no one would be stupid enough to make a mistake like that. And I thought so for many years, until the very day when I made that mistake. Because what I did is I copied a largish amount of code, and then I had to rename one of the variables. And so I renamed all of the A's to B's, except I missed one. And there I had code that acted very strangely. And it was hard to find, because your eyes don't normally look for this kind of stuff. You know, I had a page full of code. And I thought, this was really horrible. Why did they do that? Why don't they make it so that find, they just pass the vector? The vector knows how long it is. It's a vector. So why does find insist on having two iterators instead of a vector? And so the reason I thought that they taught you this is because they spent a great deal of trouble in Inf2 to teach you all the building blocks that led to it. So you know about arrays and pointers. You know about templates. Find is a template. So find is a template that was written so that it works at the same time for arrays and for vectors. The very same template. So find, there's only a single find that was implemented, and it was very cleverly implemented with all of the things that they taught you, templates, specialization, so that this stuff works automatically. And so for a C array, what's an iterator is a pointer to the beginning and a pointer past the end. For a vector, it's this kind of thing. So what you have to realize when you use the STL algorithms, and they're good algorithms, you want to use them, you have to realize that they're not as good as they could have been because they were designed to be simultaneously usable for vectors and for arrays. Now the mystery is, why did they do that? Did they not know that nobody uses arrays? But it looked so cool at the time. It was a poor design thing. What they should have done is they should have said, fine, maybe we'll make a version for arrays, but they should have made a good version for the safe data structures, a good and safe version. Now, there are implementations of STL that you can find that do checking, and it's worth looking for them when you use the STL. But so it shows that many, many years ago, when C arrays made some sense, before C++ was built on top of the Cinquecento, where this kind of ceased to make sense, they still influenced the design of such important things as the standard library. And so it's good to know that that's the reason, and that's why you have to have this kind of pain with this begin end iterators and stuff. One day they should really fix it. It wouldn't be a hard fix. All right. Now you've learned a little bit about objects. And so when C++ was designed to give modern object-oriented programming on top of the foundation of C, it gave us lots more opportunities for traps. So here's one. I have a point class. You've learned about constructors in AST1? Yes? Yes? Okay, so here's a point constructor, and so it has a couple of default arguments. So when you don't specify y, it gets defaulted to 0. If you don't specify x, it gets defaulted to 0. And here I'm making 3 points. P, Q, and O. O is the origin at 0, 0. Or do I? How many points were constructed? Two. Why 2? What is this? It's a function prototype. It is the prototype of a function O that consumes no arguments and returns a point. Isn't this terrible? Isn't this totally disgusting? So the syntax is so overloaded that you can't tell the difference between a point. You would have had to declare it as point O semicolon, right? That would have been correct. So that's really bad. But it gets worse. Here I have the very same point class that you've just seen. So I'm constructing a point out of its polar coordinates. So I have a length and an angle, and so here is my cosine. You know this thing, right? So polar coordinates, theta, r, and then x is cosine theta, and y is r sine theta. So does it work? Of course it doesn't work, or I wouldn't show it to you. Why is the y component always 0? If it was, then that would be my mistake, but that's not what I had in mind. Yeah?
No idea, but does it work if we put the brackets instead of parentheses?
Where? Here?
Yeah, for example, no, not parentheses, but like curly brackets.
Like this? No. So when you look at how you can construct a point, you can't construct a point out of an array because it takes two numbers. So the curly braces would not compile. But what's weird about the declaration? How do you normally construct a point? Yeah, why does it only take one? So you're on the right track. It only takes one.
Comma is the operator of
Excellent. This thing here is the comma operator. Another totally idiotic feature of C. So if you remember the comma operator in C, when you have two expressions, A comma B, someone said when they designed this language, they had this bright idea to say, oh, we'll just make this execute A, and then we throw it away, and then we make it execute B. Why did they do that?
wanted something to be computed, return the result.
It's like a shitty version of function composition.
Well, not even that. They had a very specific reason, and that reason is that you should be able to say I++, comma J++. They wanted to be able to, this thing here, in a for loop, it takes an expression, and they wanted to be able to say, what if we want two things with side effects in an expression? So if you have a for loop that increments both I and j, and you want to then, you want to put that in the last slot of the semicolon, there's not enough room from the syntax to increment both I and j. And so they said, oh, we'll just make the comma operator do this. So this seemed like a bright idea at the time. And so as a golden rule of language design, if you as the designer of a language have a bright idea, what should you do?
Ignore it.
You should take a long, cold shower and wait for it to go away. Right? So this was one of those ideas that sounded really good at the time. But of course, look at it here. Here we have a comma operator. Really, what I should have done is I should have omitted this equal sign. Right? Then it would have called the constructor in the normal way, and the comma would have separated the two parameters. But I have this equal sign. So the equal sign is there, and so it now evaluates the thing on the right-hand side. The thing on the right-hand side is not a pair, but it is something comma something else. So it computes r times cosine theta, throws it away, computes r times sine theta, and now it uses the fact that you have a default argument to call the constructor with r times sine theta for x and 0 for y. It compiles and it runs, and all of the points lie on the x-axis. I remember when this happened to me, and when I looked at the display, so I constructed a whole bunch of points in this way. I looked at the display, and they all lay on the x-axis, and I immediately knew what I had done wrong. But this is a really terrible, terrible confluence of multiple bad design decisions. The two bad design decisions are the comma operator, not so good, and the second bad design decision is the following, that if you have something, notice that there's no constructor here. It doesn't say point or something. But in C++, when you have a constructor that is capable of taking a single value, that's also used as a type converter. You're going to learn that next semester, and it's going to make you cry. So it will take this number and then invoke this constructor. So it is bad. So I want to talk a little bit about inheritance, which is something that you haven't really seen, to alert you to another very unpleasant aspect of C++. So I'll teach you all about inheritance in 30 seconds. So you know what a class is. You've seen the class point. The point has an x value and a y value. And now let's say we want to have a diagram. We have some points in here. But maybe what we actually want to do with these points is we want to have a label for them. Maybe there's a country. And so then we want to say a labeled point is just like a point, except it also has a label. That construct is called inheritance. Whenever you say something is just like something else, but it also has, then we want to say we want to inherit from the point. That means we get whatever capabilities we already have for the point. Maybe the point class has some member functions that do something useful, move the point around or whatever. And then, then it should also move the point with the label around. That will then be automatic. And so the syntax for inheritance in C++ is a little weird. You'll just have to live with it. This thing here means inherits. Just deal with it. It's the way it is. So colon public is C++ speak for inherits. So a labeled point inherits from a point. When you inherit, you say, what are my new variables? And now a point has a label. It also has an x and a y, because it inherits them from the parent. Just like you, in fullness of time, will inherit whatever your parents have, an object inherits from its parent. Now, we'll define a method. So here we'll say to print a labeled point, we will want to print the x and y of the base class, and there's already a method to do that, and we call that method. And then we print the label. Now, this isn't going to work, but since you have really no way of knowing that, so I'm just going to tell you why it's not working. So in this case, the comment is wrong. What does this print actually call? It calls itself, right? There's no other way of knowing it. And so what you have to do is in C++, you have to say, I want the print function of point. Then it calls that one, which prints x and y, and then it prints the label. All right, let's try this again. What's wrong? Printing the point, the base class method, and printing the label. No, not you, someone else. Yes. Aha! What? There should have been 2 colons. So you remember this from the previous slide? There were 2 colons, and now I only have 1. Why does it compile? Does it really not care about the colons that much? Can you always take out half of your colons? Would they then be semicolons?
It's a label.
It's a label, yes. It's a go-to label. So in C, in good old C, there is a go-to instruction. Did any of you ever use it? Did anyone ever use a go-to?
Never.
When I was a young lad and I told my mother, "Mom, I will be a programmer," she said, "You may be a programmer, but only if you never use goto." And so I never did. Never used break and continue either. I had to promise her. So, but still, it's in the language. And so a feature that you never use is still in the language, and it can confuse you. Does anyone ever make this error of forgetting the second colon? All the time. When I used to teach C++, the POO course, every semester there would be a few students who were bitten by exactly this error, who had no idea that what they were doing because their mother didn't tell them about goto, and no one else did either, sensibly. So this is kind of weird, right? So it's a syntax thing, of course. But that's all by matter of introduction. Inheritance is very important. It's a way of modeling a system. You start out with some basic classes that do something. Someone programs those basic classes to do that job well. And then you can take those existing classes, inherit from them, and then build bigger systems on top. A typical practical application is you might want to build an application with multiple windows, like a graphical user interface, and you will use a toolkit that gives you a base class for a window. And you will say, my window is just like the standard window, except it shows something particular on the screen. Or my button is just like a standard button, except when you press it, something particular happens. And one typically uses inheritance for this. One says, I want to take this window, I want to take this button, I want to form a subclass of it and add my own behavior for it. And the great thing is, I as the programmer don't have to know anything about how windows and buttons work. Windows and buttons are complicated. You know, when you press it, it looks a little different and stuff. And this is all stuff you don't ever want to program. You want to inherit that. Just like in real life, right? I don't ever want to have to save from my own house. My parents did that. So inheritance is a big, big thing. One of the things that you want to be able to do with inheritance is you have your inherited object, and now you want to pass it along to some code that works with either a base object or some inherited object. And for that, you have to use pointers. So over here, for whatever reason, this is just a dumb example, print2 wants to work on 2 points. Here, I'm just printing the 2 points. Maybe I should have done something better to draw a line between them or something. And so it takes these 2 points, but now I want to call it in such a way that I can call it with points or with labeled points. More practically, you might want to have basic buttons or the buttons that do your special behavior. And you always have to use pointers when you do that for a simple reason. That let's say that you are a function that the print2 function here, if I were to pass this thing without the new, then the sizes would vary. A labeled point has more information on it. And so if you push them both on the stack, then the function would not be able to access them. But when you access them through pointers, then the function gets 2 pointers. One of them is a plain point, just with an x and y, and the other one is a labeled point with an x and a y and a label. And pointers are essential to make this work. That way, when a function receives a pointer, it knows, oh, maybe it's a pointer to a point or a pointer to a labeled point with more stuff further down behind the point stuff. As long as all it does, it uses the x and y, then it doesn't care what's after it. That is how inheritance is implemented in C++. When you give something that may be either a base or a more refined object, you don't give the object, you give a pointer to it, and thereby the caller can use the base features that it knows about and ignore those features that it doesn't know about. Works perfectly nicely. It works like that in Java and in Python as well. In all of those languages, when you give an object to someone, you always actually give a pointer to the object so that this what's called polymorphism can work. Polymorphism is a technical term saying you get something that may be one or a similar thing, and you don't need to know. Pointers make it work. So as much as we complain about pointers, they're super useful for stuff like that. Now here I have a different function here. Here, for whatever reason, I have an array of points, and I want to print them all. Or might want to paint them all, or make a cloud of them, or whatever. And now, so remember, C++ was invented so that one can do modern large-scale programming, that one can do things with objects and with inheritance. And it was built on top of C because people were familiar with C. There was an infrastructure of existing C compilers, of C programs out there, and so on. And now you're going to see that on the one hand, you have object orientation and large-scale programming. On the other hand, you have a language that was designed to replace assembler. And when the two are mixed together, something terrifying happens. So I'm going to do this very slowly so you see just how terrifying it is. So I have an array of labeled points here. Let me make a picture. Here's my first labeled point, my second one, the third one, and then I'm not going to draw the rest. So it has an x and a y and a label, and an x and a y and a label, and an x and a y and a label. That's my array of 10 labeled points. I now pass it to print all, and what does print all get? Print all has 2 parameters. So the parameter n will be set to 10, and then it has a parameter points. And what is points set to? To a pointer to the initial element, right? That is what's called array pointer duality, right? When you pass an array to a function, the function receives a pointer to the first element. So now let's look at what this function does. It's going to call print to print the first point. And that is going to say, okay, here we have a point, it has an x and a y, and it's going to print them. Then it's going to print points bracket 1. So it's going to compute the address of points bracket 1, which is where? You know what it is. It's star of points plus 1. And points plus 1 points where? It points 1 point further. The size of a point is whatever the size of this xy. So points plus 1 will point right here. in the middle of an existing object, and so then towards the first half of the following object. Nothing good can come out of this when it prints, right? Now this sounds totally terrible. So this will crash and burn, or it'll print total garbage, or something. This is not what large-scale programming is all about, right? So here you have an object-oriented programming language where the most basic of things do not work. So a conversion from a subclass to a superclass, that is the bread and butter of any object-oriented programming, and it interferes here with something else much more primitive. So let's see why it even works. Yeah, so it's total absolute disaster. Why does it even work? The compiler has a type checker. Everything has a type, and it is the goddamn role of a type checker to make sure that only those programs compile that actually kind of type correct. That's how type checker works in every other language, except C and C++. And so let's see what happens here. So what happens when LPS here gets converted into points? Then first of all, it says, what is the type of LPS? Oh, it's an array of labeled points. So it's a labeled point array. That gets converted to a labeled point star. That's array pointer conversion. That gets converted to a point star. That's the object-oriented conversion to the superclass. That gets converted to a point array. That is the conversion from a pointer back to an array parameter. One of these conversions is semantically correct, and that's this one here. You could even argue that this conversion here is semantically correct, because if you have 10 labeled points, surely you have one. This conversion, on the other hand, is terrible. It simply does not make any sense to say, just because you have a pointer to a single point, that you should be able to assume that you could have a pointer to more than one point. So you have these two conflicting notions in C++, that a pointer to a point means maybe it's a point, maybe it's a bunch of points. Or you say a pointer to a point means it's a point or it's a smarter point. Either it's a bunch of or it's a smarter, but you can't mix the two. It makes no sense. And yet they do. So this is really terrible, and it makes you it makes you think about what C++ and C and all these languages what they're about. So let's see what we can learn from this. The first smaller scale lesson is that syntax matters. It is awfully nice to have a language with decent, predictable syntax. That syntax that is full of traps, where you have to look hard what the meaning of something is a problem. And it's not just C and C++. A language that I know well is called Scala, and it's a very nice language. But there is something wrong with Scala. Every once in a while, me and my colleagues look at we project some code, and we scratch our head for 15 minutes to say, what does this actually mean? What is this comma and this dot and this colon? What do they actually mean? And that sounds kind of bad, right? I mean, if grown men have to waste their time with that, there is a problem with that, and it's worth recognizing that problem. It is a negative aspect of that otherwise fine language. So in C and C++, you have plenty of syntax, little issues that are there because unfortunately the designers of these languages were not all that skilled and didn't really pay much attention to it. And what's particularly sad then is that some of these syntax things exist in Java that picked it up from C++, that picked it up from C. And so they never go away. So the people who designed C have had a horrible negative impact on millions and millions of programmers just because they didn't figure out what the people did right before them. So, but that's syntax. Syntax is something that people have learned to live with. The other lesson that I really want you to think about is that what you have in C with these unchecked pointers is not just a little bit dangerous. It is really, really, really dangerous. So when you have a pointer, when you see T star, what is the first emotional reaction that is reasonable to have in this context? Fear. Okay, the rational response is to say, this does not look good. There better be a good reason for this, and I have to be very careful. And you know that from your own programming experience. That, it's difficult to understand what they do. It's difficult to reason that they're technically correct. They often aren't technically correct. And attackers will exploit this. Every day, your Windows machine is under attack from someone who tries to download some program that tries to attack some Windows driver where someone didn't do this right. So unchecked pointers are really dangerous, and you have to respect them. You also have to understand them. There's no way around it when you do C programming, and even with C++, oftentimes they're there. You have to understand them. And that's the reason that your instructors torture you with 2 semesters of Inf1 and Inf2. It's not just that they hate you. They actually want you to know this stuff. So you get into this great level of detail on how pointers work because they are ubiquitous, but they are really dangerous. And they are dangerous because normally one would not design a language that exposes them so often, but by historical accident, we have them in C++, which otherwise is a useful language. And we certainly have them in C because its ambitions are not safety, but high-level assembly. Now, if there ever was one bad idea in programming language design, if there was ever one idea that was so much worse than every other idea, it is pointer array duality. Nothing charitable can be said about pointer array duality. It is difficult for people to understand. You have to know these rules, that star p plus n is p bracket n, and it buys you nothing. It buys you exactly nothing. You get no safety out of it. All you get is a confusion between what should be 2 unrelated features, namely pointers and arrays, and but it's there. We can't change history. There's lots of software that's built with these things, and we just have to accept it. But I find it personally easier to accept, to know that it was a dumb idea than not to know that. So when using C++, you do have the great luxury that inside the C++, inside the vast territory of C++, there is a pretty good language inside if you stay away from the bad parts. Don't use arrays, for example. You know not to use gotos. And so everyone who uses C++ in a professional way, they usually have some kind of a style guide, some kind of a approved subset, some kind of a standard. You can go to Google, for example, and see what the Google engineers, what they have agreed, which features of C++ they use, and which features they don't want to use or only use in dramatic circumstances. And that's a very good idea. So when you use C++, for example, and you always use vectors or you use the array template, if you use some of the other high-level containers that you have, if you use the STL algorithms and are aware of its pitfalls, it's a perfectly good language. It's fast, it's efficient, it has good tooling, and there's nothing at all wrong with C++. Just don't mix it with low-level C. There's no benefit in that mixture. It's just a risk. No. When using C, and again, there are many, many good reasons to use C, it really, really helps to understand what every statement does in the machine. When you understand what a pointer does, when you understand what p plus I does and star p and all of that thing, when your fingers and your brain are wired so that when you type this along, that you have made that connection, then C is fine. There are many people who use C every day and who do that. It's a high cognitive load. There's a lot of things that you have to keep in mind, and you're going to be less productive in terms of writing large amounts of functionality. But if you need to write small amounts of functionality that execute as quickly as possible, sure. It's a reasonable language. So they're really 2 different languages, and I guess that is where I disagree with people who say you want to learn them together. You want to say, this is the C way of doing it, and this is the C++ way of doing it. Because they are very different. So you're much better, in my view, to say, this is the best way of doing it in C++. That is the best way of doing it in C, and not thinking so much about them in parallel. But whatever. So definitely use C when you profit from the use cases. Use C++ when you profit from the use cases. But also know when you don't. So just a few days ago, someone said, oh, I've programmed this user interface in Qt, which is a C++ toolkit for doing user interfaces. And my first reaction was, what? Because the rest of the program didn't involve any C++. There was no reason to use Qt. You can use a Java toolkit, or even better, you can just use JavaScript and have the stuff rendered from the web, which is what everyone does. So it seems crazy to say, just for that, I'm going to use, what is a potentially dangerous toolkit. Of course, I've seen other people who use Qt because the rest of the program was written in C++ and it was a very good match, and then it makes a lot of sense. But you really want to, when you employ a programming language, you want to think about what are the risks versus what are the rewards. And it's not just C++. I'm just telling you about C and C++ because those are the two languages that you know. Pretty soon, someone is going to say, hey, I know what we're going to be doing. We're going to be doing this in JavaScript. And
Sounds like a bad idea.
yeah, right. I mean, so then you have to say, why? And in fact, there is a very nice picture that's me making the rounds on the web where there's a book called The Standard JavaScript Reference, about this thick.
And the good parts.
Yes, and next to it is JavaScript The Good Parts. There's a book called JavaScript The Good Parts, and it is this thin. So it's a little bit unfair because the JavaScript book has all the library as well in it. But still, so JavaScript is another one of these languages that has a lot of weird parts and some good parts. And you don't just want to use JavaScript because it's cool or because there's Node.js or whatever. You want to use it because you're taking advantage of its strengths. It runs in the browser. Everyone has a browser. Everyone can run it. That's great. But for JavaScript on the server, I mean, why, right? So every language has its terrible points. And so you want to know when you choose a language, what are the risks versus what are the rewards. You're just in this interesting position where you start out with two what happen to be the more dangerous languages out there, and you learn both of them at the same time. But it's going to happen to you all your life that you're going to have to make these decisions. So languages are human creations. They have the good parts. They have the bad parts. You want to know the bad parts to protect yourself from them. And so next time you get to learn a new language after you've gotten the basics, find the puzzler book, find the traps and pitfalls book, and have fun, have a few good laughs with your friends to see who can solve these first. All right, thank you very much.